Chapter 20, Lesson 6. In this lesson, we'll take a look at a version of a battery called an electrolytic cell. And this essentially is kind of the opposite of the voltaic cell that we've looked at. Remember, a voltaic cell is simply a battery stocked with two reactions which transfer electrons, and that those electrons can be used to do things and provide energy. Well, we can actually reverse the system. We can, by putting electric current, electrical energy through a system, we can make it go in the opposite direction. So we can make things oxidize that don't usually oxidize. We can make things reduce that don't usually reduce. And the example here is, if you take a look at chlorine, chlorine will usually want to gain electrons and become chlorine minus. This is actually why you rarely find chlorine in nature, because chlorine is very reactive. However, we can get chlorine for ourselves by driving electricity through here. So in this effect, you're reversing the reaction. Same thing with sodium. Usually sodium is not found in its nature in its elemental state. It's usually found as sodium chloride, but we can make it into regular sodium by reversing the reaction. And this is done essentially the same way, but backwards from a voltaic cell. So why don't we take a look, and here it says go ahead and write the overall reaction that's occurring between the two half cells in the diagram. So what we're seeing is electrons are flowing this way, which means electrons are coming onto this surface, and sodium ions are getting reduced. This is the opposite of what usually happens. Sodium usually gets oxidized, but here we're making sodium get reduced. So sodium goes from +1 to elemental sodium, and the chlorine actually gives up the electron. Chlorine gets oxidized, goes from Cl minus up to Cl2. So chlorine goes from -1 to Cl2. Again, this is the opposite of what nature would do. And this is why we have to use a battery. We have to drive electricity through the system. So to write the overall reaction, let's simply balance these two half reactions. We'll require an electron on the left side here. We'll require 2 electrons because we'll have to first balance for the 2 chlorines, and then we'll have to put 2 electrons on this side. We'll have to multiply the whole sodium half cell by 2. So let's go and write this up here. We have 2 electrons plus 2 sodium plus, giving you 2 sodium. This is out. And now we can combine these two reactions into an overall reaction. So we have, and our electrons will cancel out as we combine this. This is again balancing an equation. We've done these in the first few lessons. And we end up with 2 chlorines plus 2 sodiums, giving you Cl2 and 2 sodiums. And this overall reaction is actually showing that chlorine is getting oxidized, and sodium is getting reduced. Now what you can do, you can even determine the cell potential of this system. Now the cell potential will actually be negative. If you do cathode minus anode, you'll see it's going to be negative, and that will tell you how much electricity, what kind of voltage of battery you would need in order to make this happen. So this is actually a practical thing. You could look up the reduction potentials and do cathode minus anode and get a potential for your cell, and it will be negative. And it will be negative because it is non-spontaneous, because nature will not make this happen. That's the idea. Okay, we're going to wrap up the chapter with some considerations of stoichiometry. And I know you've waited for this moment when we can apply stoichiometry to electrolytic and voltaic cells. And to see how stoichiometry connects here, we have to write out our half reaction. So consider this half reaction. What we're doing here is we're actually taking magnesium 2+, which could be found in nature, in salt water. Ocean water oftentimes has a lot of magnesium. And then we can make pure magnesium. And everybody loves pure magnesium. So the way we make it is actually by adding 2 moles of electrons to a mole of magnesium 2+. So it takes 2 moles of electrons to plate out a mole of magnesium. That's what this balanced equation is showing us. So we're going to actually be able to calculate how much mass of metal, say, will produce by going through the electrons. And electrons will connect us to the electricity. And a mole of electrons, recall, was a Faraday. We introduced this constant as a mole of electrons, which is 96,500 coulombs. And this is simply the charge if you have a mole of electrons. And then we're going to find one more new relationship, and that's an amp. Amperage, you may have heard of amperage if you took electronics or something like it. Amp is actually current, and current is how fast the electrons flow. So an amp is defined as a coulomb per second. It's per second, it's rate, so how fast it flows. So say if you were to get yourself a 2 amp device, then it needs 2 coulombs per second flowing, which means it needs quite a bit of electrons to get it to work. So we're actually going to use these definitions to be able to solve a problem, and we're going to do a few problems and we'll kind of wrap it up. So here's how we would use stoichiometry with electrochemistry. What mass of magnesium is formed by passing a current of 7.10 amps through molten magnesium chloride for 1.70 hours? So again, this is the same magnesium that we just saw. So what we need is, we've got magnesium 2+, to which we're adding 2 moles of electrons and producing magnesium metal. And again, we're producing 2 moles of magnesium, and we have 2 moles of magnesium here. And actually, if you take a look at the reaction, we don't need 2 and 2. That would be too many. These should not be there, actually. There it is. So what we'll do is we're asked to solve for the mass of magnesium. Now we're going to go through the electrons. We're given 7.10 amps, and remember 1 amp is actually 1 coulomb per second. What we'll do is, let's find out how many coulombs how many coulombs per second we've got. Let's convert these hours into seconds, and then we'll use the amp to find out how many coulombs we actually have, because our connection is that 1 mole of electrons, which is 96,500 coulombs, is equal to a mole of electrons. In other words, we're going to go from amps to coulombs, and then from coulombs to electrons, and then from electrons we'll go to moles of magnesium. So it'll be a few steps, but let's go ahead and do this. So 1.70 hours. Let's go ahead and convert that into seconds. An hour is 60 minutes. We're using dimensional analysis here. And a minute is 60 seconds. So let's first calculate how many seconds we have. Go and calculate that out. We should get ourselves 6,120 seconds. So we're going to use this number here. Next, what we're doing is we're actually running the thing for this long, and every single second we get 7.10 amps. So to find out how many coulombs we have, we'll have to multiply. And if we have 7.10 coulombs per second, that's the definition of an amp, coulomb per second, multiplied by 6,120 seconds. The seconds will cancel out, and we'll find out how many coulombs we have. So multiplying these two numbers gives us 43,452 coulombs. This is the charge that's being put through the system. Now we know the relationship between coulombs and moles of electrons, so let's go ahead and use that to find out how many moles of electrons this actually is. We know that 96,500 coulombs is equal to 1 mole of electrons. We'll see what that gives us. So go ahead and take this number and divide it by 96,500. This gives us 0.450 moles of electrons. And the rest of it is stoichiometry, So based on the equation, 2 moles of electrons produce a mole of magnesium. So we'll put 2 moles of electrons at the bottom, 1 mole of magnesium on top. It asks us to go to mass. So let's go ahead and do a mole of magnesium equals 2431, is it? Double check your favorite periodic table. And it is 2431. My favorite periodic table says 2431 grams. Go ahead and calculate the rest of it and see what we get. Divide by 2 times 2431. And we get 5.47 grams of magnesium. So this is how much pure magnesium you can actually make by passing this much current through for 1.7 hours. You get yourself 5.47 grams of magnesium. This is pretty neat because you can connect the chemistry to the electricity. Again, the amperage is how fast the electrons flow through it, and from that we found out how many coulombs that would take. From that we found how many moles of electrons, because a mole of electrons is defined as a number of coulombs, and then we were able to compute the mass. Let's do one more example problem. Let's flip it. Here it says, how long will it take to plate out 25 grams of magnesium using a 2.40 amp current? Again, our reaction is we're plating out magnesium, so we need 2 moles of electrons to produce a mole of magnesium. And here, essentially we're going to go backwards. We're going to go from grams to moles of electrons, from moles of electrons to coulombs, and then we'll finish up with time. So we're going to solve for seconds here, or seconds, eventually hours if we need to. So we got 25 grams of magnesium. Let's go and convert to moles of electrons. 1 grams is a mole of magnesium. Based on the equation, 2 moles of electrons for 1 mole of magnesium gives you 2 moles of electrons. Apologize. And let's go ahead and compute how many moles of electrons we've got. So let's go ahead and just do this portion. So do 25 divided by 2431 times 2. So we got roughly 2 moles of electrons, 2.06 we could say, 2.06 moles of electrons. Now to get to amperage, recall that we said that a mole of electrons is a Faraday, or 96,500 coulombs. We're going to get to charge, so we got 2.06 moles of electrons multiplied by a mole of electrons produces 96,500 coulombs. So let's see how many coulombs this gives us. Go and multiply it. 96,500. That gets us 198,000 coulombs. Now we're going to be, so this is 198,000 coulombs. We're going to be running it for, we're using a 2.40 amp current. So remember that an amp is a coulomb per second. And so we got coulombs here. We can actually convert to seconds by dividing coulombs. So if you do this using dimensional analysis, it's 198,000 coulombs multiplied by, coulombs have to go on the bottom, seconds have to go on top. So we got, in 1 second, we got 2.40 coulombs. That is our amperage, because an amp is a coulomb per second. So notice I just put this on the bottom here so that the units match up. Dividing those two, we finally get ourselves 82,700. In this case, seconds. and nobody likes to express time in this many seconds, so why don't we just convert to hours. So 82,700 seconds. It's still 60 seconds in a minute by Babylonian reckoning. Still 60 minutes in an hour. So divide the two, and that's a little better, 22.97 hours, or 23 hours. So set it on automatic play, and go take a nap, and you'll come out with 25 grams of magnesium 23 hours later. So these two example problems showed us how to connect electrochemistry with stoichiometry, and this should complete for us lesson 6 of chapter 20.